Welcome back again. We have learned about the vacancy diffusion. Now let's talk about the interstitial diffusion. The interstitial diffusion is the second type of diffusion, which involves atoms that migrate from an interstitial position to an unoccupied neighboring site. This mechanism is often used for interdiffusion of impurities, which are smaller than the host atoms, such as hydrogen, carbon, nitrogen, and oxygen. This figure demonstrates the interstitial diffusion mechanism. As the size of the impurity is smaller, it cannot replace the host atom. So, in most metal alloys, interstitial diffusion occurs more rapidly than the vacancy diffusion because now the interstitial atoms are smaller and thus they are more mobile. However, there are more empty interstitial positions than vacancy positions. Hence, the probability of interstitial atomic movement is greater than for vacancy diffusion. Now, let's see how can we quantify the amount or rate of mass transfer. We begin with the statement that diffusion is a time-dependent process, which means the concentration of atoms that is transported is a function of time. The rate of mass transfer can be expressed as diffusion flux, which is known as J. The diffusion flux is defined as the mass or number of atoms diffusing through a unit cross-sectional area of a solid, which is of course perpendicular and measured per unit time. Mathematically, diffusion flux may be written as J equals m over A T, where m is the amount of number of atoms or molecules diffusing, A denotes the cross-sectional area, and T is the diffusion time. Its units are kilograms or atoms per meter square per second. If you want to measure the diffusion flux empirically, then you need to do an experiment. You have to make a thin film or membrane of known cross-sectional area. You have to impose the known concentration gradient, and finally measure how fast atoms or molecules diffuse through the membrane. Typical situation, or one of the typical situations, is shown in this figure. Now let's see the net flux diffusing under steady state condition. This happens after some times when the diffusion takes place at a constant rate, which means the number of atoms entering is same as the number of atoms leaving the membrane. Under this situation, the rate of diffusion is independent of time, and the diffusion flux is proportional to the concentration gradient, which is dC over dx. So we can write J equals minus d dC over dx. This equation is known as Fick's first law of motion. The constant d here is known as diffusion coefficient, which has a unit of square meters per second. The negative sign in this expression indicates that the direction of diffusion is from high concentration to low concentration. When concentration C is plotted against the position or distance within the solid X, the resulting curve is termed as concentration gradient profile. Moreover, the concentration gradient is the slope at a particular point on this curve. In the present treatment, the concentration profile is assumed to be linear. Sometimes it is important to define a term which is known as driving force. This term is very important in diffusion. This term is a factor that compels diffusion to occur. For Fick's first law of diffusion, the driving force is the concentration gradient. Purification of hydrogen gas is one of the practical examples of steady-state diffusion. Here, one side of thin palladium sheet is exposed to a mixture of gases composed of hydrogen, nitrogen, oxygen, and water vapor. Hydrogen selectively diffuses through palladium sheet to the opposite side, which is maintained at a constant and low hydrogen pressure. Now we will consider the diffusion in non-steady state condition. This is the case when the diffusion flux depends on time. Many practical examples are non-steady state, which result into a net accumulation or depletion of the diffusing species. Under this condition, we mostly use Fick's second law of diffusion in the form of partial differential equations. Fick's second law of diffusion can be expressed as partial C over partial T equals D partial square C over partial X square. One example of Fick's second law can be seen in this figure, where the rate of diffusion is a function of both distance as well as time. As we can see, the diffusion of copper atoms to aluminum with different times, that is T1, T2 and T3. Here T3 is higher than T2 and T2 is higher than T1. With the increasing time, the concentration profile becomes more and more linear. Moreover, the concentration gradient also increases if we use a mixture of gases, such as given in the example of hydrogen purification with palladium. Now let's examine the factor that influence the diffusion rate. The magnitude of the diffusion coefficient is indicative of the rate of atomic motion and depends on the size of both host and diffusing species as well as on the microstructure and temperature. The diffusing species and the host material influence the diffusion coefficient. For example, there is a significant difference in the magnitude between self-diffusion and carbon interdiffusion in alpha iron. As you can see in this figure, at 500 degrees Celsius, the diffusion coefficient D of carbon interdiffusion is very high. This comparison provides an overview of the rates of the diffusion via vacancy and interstitial modes. Self-diffusion occurs by vacancy mechanism, whereas carbon diffusion in iron is interstitial. On the other hand, the temperature has more profound influence on the coefficients and diffusion rates. Empirically, temperature dependence is given by a Boltzmann factor, which is D equals G naught exponential minus QD over RT. Here, D is the diffusion coefficient, D naught is pre-exponential function, QD is activation energy, R is gas constant, and T is the absolute temperature. For example, for the self-diffusion of iron in alpha iron, the diffusion coefficient increases exponentially, nearly 6 orders of magnitude when the temperature is raised from 500 to 900 degrees Celsius. The activation energy, on the other hand, can be thought of as that energy required to produce the diffusive motion of 1 mole of atoms. A large activation energy results in relatively small diffusion coefficient. The previous figure also shows the diffusion of various elements in alpha iron as a function of temperature. Here, a graph of logarithmic diffusion coefficient versus reciprocal of temperature is plotted to estimate the values of D naught, QA, and R by linear fitting. We must also note that the atomic diffusion or atomic migration may also occur along dislocations, grain boundaries, and external surfaces. These are sometimes called short circuit diffusion paths. Here, rates are much faster than for bulk diffusion. However, in most situations, short circuit contributions to the overall diffusion flux are insignificant because the cross-sectional area of these paths are extremely small. Now, let me give you an overview of this lecture. In this lecture, we have learned about basic mechanisms of diffusion, which are vacancy mechanism and interstitial mechanism. We have learned that interstitial diffusion is faster than vacancy diffusion. We also learned about Fick's first law and second law of diffusion. In addition, we saw that the diffusion species and temperature are the two important factors that define the diffusion rate. Last but not the least, we can conclude that diffusion is faster for open crystals, materials with secondary bonding, smaller atom size and lower density materials. On the other hand, diffusion is slower for closely packed structure, materials with primary bonding, large atom size and higher density materials. Alright, so this will be the end of this chapter. Thank you very much.